Hello and welcome to 1-4 in our geometry section. We are going to be talking about angle measures in this particular lesson, and this should be a good one. Let's start with our first definition, and that is a ray. This is going to be our third version of a line, and it's actually kind of cool because if you remember, I'm going to put this in pink. A line has two arrows on both ends, which means it goes on infinitely in both directions. We also talk about segments, which has no lines or no arrows on both ends. An array, this one you actually could put in black, has one endpoint and one arrow. So it's kind of a combination of these two. The interesting part is it does go infinitely on in one direction because of the arrow. So we have a length array that goes on forever, means the length is infinity. So with that said, we actually need another endpoint. It's not an endpoint, we just need another point here, but just know that array, one endpoint, and then one point, and then the arrow is on one end. So, for instance, if I were to name this, for instance, let's say DG, this ray would be called DG. And array, just as is specified, is part of a line that has one endpoint, and extends, let's see if I can zoom out a little bit, infinitely in one direction. So that's pretty much what we specified 2 seconds ago, and we have names for it. Well, in this particular case, we only call this one DG. The question though is, we have to draw a line above it, and since it's a ray, we only draw one arrow. And it's really, really important that you label it, the arrow end, on the same side where the arrow ends, or the arrow has the infinite loop. So you cannot name this GD, that it would be incorrect. And even if I had a third point on here that's collinear, let's say this is O, we could also name this DO, if we so choose. Because the arrow is still on that right side, it still qualifies as going infinitely to the right, and DO technically works. OD would not. That is incorrect because the D is the endpoint. It would not have an arrow in that direction. Now an angle, well, a ray doesn't have any angle, but an angle uses a combination of rays in order to create an angle. So, for instance, if I were to name, or let's draw another ray, and I'll put a point here, and let's call this one A and T. Now, like I said, a ray by itself is not an angle, but what happens if I add another ray? And let's put in here a C. Well, we now have an angle. It is the measure that is formed between, or I guess we could say, formed by, let's say this, formed by two, oops, that's too low, non-collinear, and there goes one of our definitions again, rays, so they're not the same ray, and have a common endpoint. And in this case, our common endpoint is A. End point. So in this particular case, our A is the common endpoint because we have two rays. We have ray AC, and we also have ray AT. And A would be that common endpoint, and we actually see a ray that gets formed, an angle that gets formed right at A. Okay? Now, you could also name this angle. So this is the names of the rays. If you want to put rays here, that's perfectly fine. But let's look at this angle. And I should have done this one in red. This should be in black. Let's do that. Rays, because they were in black. And then angles, there are a lot of different ways to name this angle. You could just name it angle A, and note this symbol is used for angle. It's a symbol for angle. Okay. We also have, I didn't even write it, angle A, because it is the middle point or the vertex, or it's the tip, or it's where it changes direction, all of which happen at the same point. You could also name it using three letters. You could say it's angle CAT because you follow the measure. You could also call it angle TAC if you follow it the opposite direction. It still creates that angle and you're still good to go. Okay? But if you notice, A is in the middle, A is also in the middle, and here we have A just by itself. So that's a very, very common feature with this. It would be incorrect to say ATC, because that wouldn't make much sense. That's not the angle we're talking about. That would not work. And I didn't even put an angle measure here. So that would be wrong. Sometimes you actually see numbers here as well. For instance, if I put the number 1 here, you could also call this angle 1. And you'll see that pretty frequently in diagrams where an angle measure has a number next to it. Now, that doesn't mean that's the angle measure. That just means it's angle 1. It's a name. It's a different name for it. So these are names of angles. Oops, I should have put names here. So that is how angles are formed. Two rays. Okay? And we have a lot of different types of rays. A lot of different types of angles. There are 4 to be exact. There are 4 types of angles. And these should sound familiar. First one is when an angle is less than, between 0, I should say. So I'm going to put a marker here, and I'm actually going to use this Greek symbol called theta. It is literally an O with a line through it. And I'm going to put this here. We call this theta, which just means, and this is Greek, and it literally just means angle. The variable, technically, it's a Greek letter, so it's a variable, but we use it for angles. So I'm going to call that, our definition would just be angle. Okay? So theta, this acute angle, I should have left a little bit of space right above it. I'm sorry. This is an acute angle, because if you notice, it's less than 90. So that's an important feature. Theta is less than 90 degrees, but it is also greater than 0 degrees. Okay? We also have obtuse angles. That's not spelled right. Obtuse. And here we have angle measures that are bigger than 90 degrees. So theta is bigger than 90. So 90 would be here. This is bigger than 90. So interesting way. It's a different way to write it. But it also has to be less than 180 degrees. Okay? Bigger than 90, less than 180. Okay? Right angles, which we've kind of talked about, are angles that have a perfect 90-degree angle. So you have theta here is equal to 90 degrees. So here we say theta is equal to 90. That's the only feature here. Okay. And then our last angle is what we call a straight angle, where it's literally a straight line. So if you create this angle, and if you put a point right in the middle, you could say theta is equal to 180 degrees. In other words, it's a straight angle. Okay, so those are your 4 types of angles. We also have something called congruent angles. Now, we should know this. Hopefully, you can just tell by the definition of this. Congruent angles, what the definition is. Because we know what congruent means, and we know what angles are, we should be able to tell what congruent angles are. And if I were to create an angle, ooh, that's not an angle. No, not again. So let's just do it. If I were to say this is, let's go ABC. Just keep it simple. And let's draw another one. Let's point this in a different direction just to be a little bit different. And I'm going to put here 3 points, X, Y, and Z. Okay? But I'm going to put an angle tick marker. I'm sorry, I forgot the label. These are angle tick markers. I'm going to put just angle ticks. That's if I put, for instance, one angle tick, and then I put in the same one on X, Y, Z, that would mean that these 2 angles are actually congruent. Okay? And for the sake of it, actually, let's complete this triangle. Just for fun. And for fun here, let's do that. So I'm actually going to erase part of this, and we're going to do, we're going to turn this into a triangle, actually, just to make this a little bit more interesting. Okay, so sorry about that. Let's make this a little bit more interesting, and let's call this triangle ABC, and the other one's XYZ. Now, I already labeled that 2 sets of these angles are congruent, right? B and Y are congruent. So, by definition, angle B is congruent to angle Y. Okay? Now, what could also happen here is we could have another angle, but note I put 2 tick markers here, and that just means A is not the same as B. Okay? And what happens if I do 2 tick markers on X? Well, that just tells us angle A is congruent to angle X. And lastly, if I put 3 tick markers here, that just means, and same here, that just means C is neither A, it's not the same as A or B, and it's also the same as Z. So we could say angle C is congruent to angle Z. If we want a proper definition for angles, or congruent angles, and it's literally what we think it is. It's 2 angles, and I'm going to do a little shorthand here. That's angles, it looks like an L, sorry, that have the same measure. Ooh, same measure. So, last definition is an angle bisector. Okay? So, you could stop indenting. We have angle bisector. And this one's a little bit new, but bisector, if you break this word down, the prefix bi means 2, and sector just means sections. So if you take an angle and you put an angle bisector in there, if you put a bisector in there, that just means here, let's label this actually first before we start. If we were to label this LMN. So that's our angle, right? And I'm going to do an angle marker here, or angle tick mark. And I'm going to put actually a fourth point. Let's say this is going to be O. So O is directly somewhere in the middle. And an angle bisector takes this red angle. If I were to say this angle, this original angle, this whole angle, if I were to pretend and say angle LMN was equal to, let's say, 80 degrees. It's not true. It doesn't even look like it's 80 degrees, but just for the sake of it, 80 degrees. An angle bisector would make two equal parts. And it would say this becomes 40 degrees, and this becomes 40 degrees. So with that said, let's come up with a quick definition for it. An angle bisector is a ray that divides an angle into two congruent angles. So sorry for the shorthand, but it is a ray that divides an angle into two congruent angles. Okay, so using that little bit of an example, we could say, in this particular case, we have a new ray, LMO, so angle LMO is congruent to angle OMN. Okay. And this would be given, right above it, MO, that's the ray, is an angle bisector. So, with that said, the angle bisector cuts it perfectly in half. We have two congruent angles now on the bottom and top, and we're good to go. Okay? So, the last thing I do want to mention, and this was just good to know, is when you see diagrams, and I'm putting this in purple, because it's important, it's not you don't have to copy it down, but it's important to know. Diagram is assumptions. If you see, you could assume, for instance, if you see a straight line, this is 180 degrees, no matter what. If you see a straight angle, assume it's 180 degrees, okay? You could also assume if points are on the same line, they are collinear, okay? That's not terribly important. Mostly I want you to assume if you see a straight line that looks like it's straight, assume it's 180 degrees. Now, don't assume angles that look like they're 90 degrees. Do not assume this is 90 degrees. It could look like it's 90 degrees, but you need the square. You need the square there to tell you it's 90 degrees, okay? Also, don't assume segment lengths. Two segments could look like they're the same, but they're not, okay? For instance, if I drew here, they look like they could be the same lengths, but one could be 6 inches and the other could be 5.99 inches. Never assume unless you have those tick markers, okay? So that's another thing that you don't assume, that if they look like they're the same length, don't assume they are. You need the tick markers, okay? Same goes for angle measures while you're at it. If angles look like they're the same, let's put segment lengths and angle lengths. Let's put an angle. Angle measures. Don't assume angle measures are congruent. Okay? So those are things that you want to just be aware of when you're looking at diagrams. Other than that, that's a lot of definitions, I know, but they're going to be very useful throughout the entire year. If you have any questions, please let me know, and I'll see you in the next one.